So we all know that if you take an acid and dump it into some water, the pH will start at 7 and drop. And we also know that if you take a base and throw it into water, the pH will start at 7 and rise. And we also know that if you take a regular old ionic compound like salt and just make a salt solution out of it, nothing is going to happen to the pH. Well, about that. I hate to break it to you guys, but it turns out that some salt solutions, actually many salt solutions, do affect the pH of the solution. And I've got a couple demonstrations to show you what's going on. So I have a pH of, or I have a sample of salt water, and currently my pH meter is reading 5.99. And I'm okay with that because it's very difficult to get a perfectly neutral sample of water because it's always pulling CO2 out of the air and messing with the pH just a tiny bit. But I'm happy with the pH of 6 because anything from pH 6 to 8 is essentially considered neutral. And so I have a salt solution really not doing much to affect the pH. But watch what happens when I give my little pH meter a rinse and put it into a solution of sodium carbonate. Watch what happens to the pH. Wow, we're up at 11 point, almost 11.5. Yeah, there's no base in here, guys. I just put some sodium carbonate into some water, and no sodium hydroxide or anything like that. But my pH is very much in the basic region of the pH scale. All right, so fine. Maybe that's an outlier. Let's try some sodium acetate. We'll throw that in there, and ooh, wow! I'm getting a basic pH out of that. Not as basic as the sodium carbonate, but definitely 9.24 is in the basic alkaline range of that. Okay, okay. All right, let's keep going. And and finally, a quick little rinse in the distilled water and into my ammonium chloride solution, and give that a quick stir around so it has a chance to do its thing. Oh wow! And now we're down to a pH of below 5, guys. So yeah, like I didn't put stronger acid or base in any of these flasks, and yet I'm definitely getting these big swings in pH. These are just supposed to be salt solutions, and they're not supposed to do anything. Well, it turns out that some ions in solution do affect the pH, and that's the topic of this video because you're going to see questions about acid-base properties of salts, and I'm here to help you get through the calculations for those. Hello, everyone, and welcome to this episode. Today, we are learning that solutions are complicated. Just when you thought there was just the acids, the obvious ones, and the obvious bases, we find out that salt solutions can also affect the pH in some cases, and that's what this episode is about. Kind of gets a little complicated in here, so try to hang on, and I'll try to teach you a couple tricks that will help simplify these types of questions and calculations. But yes, so let's get into it. And we saw with the pH meter that some of my salt solutions actually did affect the pH. Some of them, like my phosphate solution, actually makes the solution basic. And that's because the phosphate ion actually accepts a proton from the water to make hydrogen phosphate and an OH minus ion. All right, let's look at a couple examples and then we'll try to summarize it. My ammonium solution ended up being acidic, and that's because ammonium is the conjugate acid of ammonia, which is a weak base. So it actually has acid properties because it's a conjugate acid. And it'll donate some hydrogens back and protons back to make the ammonia and some hydronium ion, and it'll set up an equilibrium like that. Okay, so again, we'll summarize this in a second. Sulfate solutions tend to be basic because the sulfate ion is actually the conjugate base um, of bisulfate ion, a weak acid. So the bisulfate ion, this is actually going in the reverse order, but it will actually make the solution basic. You might end up with a chart something like this somewhere along the line where it lists different ions and and their general properties. Okay, so let's get into it. Some ions will not affect the solution at all. And so, and as you look at these ions, you might get your like spidey sense tingling a little bit because I don't know, all of these ions that are listed here are the ions that are found in strong acids. Okay, like hydrochloric acid has this one: hydrobromic, hydroiodic, nitric, and perchloric. Those are all the conjugates of strong acids. So because they come from strong acids, they're not going to want to get their hydrogens back, and so they'll just hang out in solution as these ions. And these cations are also neutral. They don't affect the pH. And you might also notice that these are the ones that are part of strong bases: lithium hydroxide, sodium hydroxide, potassium hydroxide, and so on. They don't really affect the pH at all. On the other hand, there's a whole bunch over here that affect the pH by making it basic. And those are actually uh, conjugates of weak acids, and so on. And so this is a conjugate of a weak base, and we have a couple of extra ones over there. But yes, strong acids and strong bases dissociate 100%, and they don't really go back. And that's really the key here. So I want to summarize this in a couple of different ways. Feel free to pause the video and write this down if you want. So in general, conjugates of strong acids or strong bases have no acid-base properties in general. All right, but if they're conjugate bases of weak acids, they'll make the solution basic. If there's an ion there that's the conjugate acid of a weak base, I know it's a lot, it's getting complicated, we'll make the solution acidic. And if both an acid and a base are present, ions that will affect the pH one way or the other, the one with the higher K value is going to sort of dominate the solution. You don't see that very often, but I thought I'd throw it in there because we're dealing with it today. All right, so I'm going to pose a question here. This is a question that you're likely to see something like it in your textbook or in your class or test or something like that. And the question says, will aqueous solutions of the following be acidic, basic, or neutral? We saw with the pH meter, my pH was going up and down and all over the place. Is there a way to predict that ahead of time without actually using a pH meter? And yes, there is. Now, a lot of people get to this and they don't really know where to start. Like, how am I supposed to know if potassium phosphate is acidic, basic, or neutral, that kind of thing, all the way down the line? Well, I've actually prepared a little flowchart, and this is something that may help you. This is something that I use in my own classes, and I asked the question: will this salt affect the pH? And what you're going to do, this essentially, is break the salt apart into its cation and its anion, and I made these little boxes. And then imagine, this is where you got to use your imagination. Imagine the cation has an OH attached to it. And then you ask yourself, is that a strong base or a weak base? If it's a strong base, the cation is not going to affect the pH. But if this ends up being a weak base, the cation will act like an acid. Okay, and go over here. Put the anion on this side, and imagine in the back of your mind that there's a hydrogen in front of it, and that would be an acid. And you ask yourself, is that a strong acid? If so, the anion is not going to do anything to affect the pH. But if that's a weak acid that you end up with, the anion will act like a base. Let's see how this works with the examples from our question. The first one in the list was potassium phosphate. Okay, so break it up in your mind or on a paper or something. Feel free to copy this if you want. Put the cation here, the anion over here. Now, the cation here, that's KOH, that's a strong base. So in this case, the cation is not going to affect the pH. But on the other hand, phosphate, if you put that and put a hydrogen in it, that's actually a weak acid. So that means that the phosphate ion is a fairly strong conjugate base, because if you have a weak acid, the conjugate is actually quite strong. And so, yes, I end up with a weak acid, so the anion will act like a base. Okay, and that goes back to my first slide of this video. Let's do another one. My ammonium solution was acidic, and that's because if I take apart ammonium and chloride, ammonium hydroxide is not one of the strong bases, and ammonium is actually the conjugate of a weak base, ammonia. And so this ends up being, cation will act like an acid. And over here, the chloride, if you imagine a hydrogen on the front of it, that's hydrochloric acid. That is a strong acid, and that means the chloride itself is a very, very, very weak conjugate base, and so we have something that will not affect the pH. All right. I know there's a lot going on. I'm hoping that a flowchart like this might help. Sodium acetate. Sodium, if we put a hydroxide on it, is sodium hydroxide. That's a strong base, and so that will not affect the pH. But acetate is the conjugate of acetic acid, which is a weak acid, and so the anion will act as a base. We'll see that in one of our upcoming examples. And finally, potassium sulfate. Potassium again makes it a strong base, so that's not going to affect the pH. But sulfate is the conjugate of hydrogen sulfate, and that's a weak acid, so it will act like a base. Okay, so it takes practice, and you gotta, you're sorting through a whole bunch of things, ions, and imagining their conjugates. It's a lot, I know, but with practice, you'll get a lot better. Okay, so let's get into some calculations that you might see. So, for example, what if we wanted to calculate the pH of a 0.1 molar sodium acetate solution? We saw that sodium acetate will make the solution basic, but how basic? And how do I do that? And it's going to take a couple of steps, so follow along. In fact, I summarized the steps on this next slide. Finding the pH of salt solutions. You got to do a few things. First, determine the major species using maybe a chart like I showed you. Identify any ions that have acidic or basic properties. So see if anything will do that. Then we're going to use Ka or Kb values to determine K for the equilibrium. That's in question. We're going to solve for the H or the OH and then there find the pH. So let's check out this example again. Calculate the pH of a 0.1 molar solution of sodium acetate. So we've already found that the acetate will make the solution basic, but let's write the equation for that. So let's imagine we have some acetate ion, C2H3O2, and we add it to some water. What's it going to do? Because it's the conjugate of a weak acid, it's going to collect a hydrogen proton back to make that weak acid that it wanted to come from. Okay, that's the equilibrium that I need to work with. And I'm going to set up an ice table. By now, hopefully you're getting really comfortable with ice tables. And we're going to start with 0.1 moles of this, 0, and essentially 0 of that. I always like to let my grader or reader know that I know that it's not actually 0, but it's pretty close to 0. And we're going to set up our x values. So 0.1 minus x, x, and x. Okay, now I need to know the K for this equilibrium. And so, they give me the Ka for the weak acid, but not for the anion of that acid. And so that's pretty typical. You don't usually find charts with all the K values for the anions and cations. So you have to kind of work with it. So what we're going to do is we're actually going to go over here. And one of the things for one of the equations we use is that the Ka for an acid times the Kb for its base or its conjugate base multiplied together will always give us 1 times 10 to the minus 14th, which is Kw for water. So because this is acting like a base, I'm going to say, all right, Kb is equal to Kw over Ka, if I rearrange that. So Kw is 1.0 times 10 to the minus 14th. My Ka is 1.8 times 10 to the minus 5th for the acid. So my Kb value is going to be 5.6 times 10 to the minus 10th. And that's the K that governs this equilibrium because it's acting like a base. Okay, so now though, once I have my K value, that's an extra step you're going to have to do probably, is we're going to, actually I'll write the equilibrium expression H, C2H3O2, and the OH minus over C2H3O2 minus. Okay, that's my equilibrium constant expression. 5.6 times 10 to the minus 10th equals x squared over 0.1 minus x. And that's going to be approximately equal to just x squared over 0.1, because again, we're going to make that assumption that that's going to be very, very small in comparison. So once I get this, I get an x value, which is equal to the OH minus concentration. That's how I'm going to get my pH. 7.48 times 10 to the minus 6th moles per liter. All right, that's my OH concentration. And that will allow me then to get the POH, which is the negative log of that. 5.13. And if I subtract that for 14, the pH is going to be 8.87. I kind of skipped over those for the sake of time, but if you wanted to go back to my pH and pOH video for a refresher on that, feel free to do that. All right, and that's how, again, several steps to do, but hopefully you followed along. And now, guess what? It is time to pause the video. And I came up with another one. Let's calculate the pH of a 0.2 molar sodium hypochlorite solution. The Ka for hypochlorous acid, is Ka equals 3 times 10 to the minus 8. Take a moment, pause the video, and I'll see you back here in a second. All right, and here we go. So my solution came up with a pH of 10.41 on this one, because hypochlorite is going to act like a base, okay? And it's going to set up the similar equilibrium to the acetate ion. Similar ice table, similar Kb expression, x squared over 0.2 minus x, which is approximately x squared over 0.2. And I had to go over here and get a Kb value. So Kb is Kw over Ka, which worked out to be 3.3 times 10 to the minus 7th. Set that equal to my equilibrium expression. Got an x value, which is OH, of 2.58 times 10 to the minus 4th. Found the pOH and the pH just like last time. So if you got that, great. Good job. We're on our way to making sense of all of this stuff. So let's do another example, and then we'll do one more pause the video moment before we finish. So calculate the pH of a 0.15 molar ammonium chloride solution. We already learned that that is going to be acidic, but we now have the Kb for the ammonia, which is given. Okay, so let's do this. Ammonia, let's not worry about the chlorine, but we will worry about the ammonium ion going into water, setting up an equilibrium with its conjugate base, and it's going to make it, H3O plus. Okay, that was not my best work, but that's that's what's going to happen. So, see, again, there's a lot of stuff going on. So let's make a little ice table. 0.150 molar, 0 and 0, approximately 0, minus x plus x plus x, 0.150 minus x, x, and x. Okay, so we need the Ka value for this one, which is Kw over Kb, 1.0 times 10 to the minus 14th over 1.8 times 10 to the minus 5th. Okay, and again, I get 5.6 times 10 to the minus 10 on that one. And that's going to be equal to x squared over 0.150 minus x. All right, and again, we have a similar setup. If I solve for x, that will give me the H3O plus concentration, since that ends up being x, and that comes out to be 9.16 times 10 to the minus 6th moles per liter. The pH is just the negative log of that, 10 to the minus 6th, and that works out to be a pH of 5.03 as my answer, and I'll put a nice little heart next to that. So this one's acting like an acid. The process is quite similar, though, and following the similar kind of steps. So let's take a moment and do one more pause the video moment, a little extra challenge, and this one includes methylamine and its conjugate acid, which is part of that ionic compound. So take a moment and solve this one to see if you can find the pH. Meet you back here in a sec. And here we go. Let's finish this off. With example 4, calculating the pH, I got a pH of 5.67 because the methylamine and its conjugate acts like an acid. There's the methylamine right there. We're solving for H3O+. Again, Kw over Kb, just remember that extra little formula. That's a tool we have.